Okay, so we're going to move on to looking at something called power functions today. So power functions come from when we want to find the power of a test. So in the questions we were doing on Friday, to be able to do the power of a test, you need to know what the underlying parameter was. However, in reality, if you know the underlying parameter, you wouldn't need to do the hypothesis testing in the first place in a lot of cases. So often we don't actually know what the underlying population parameter was. So what we do is we carry out the power of the test using various different population parameters, and we can often graph them in something like this. So further away the parameter that we're using is from the true value, the more likely it is that we're going to reject the null hypothesis, and therefore it's going to be a higher power. So if we just look at an example of what it looks like. So we've got, I think we might have looked at this example before. It's slightly different question, but a similar example. We've got Poisson distribution, 3.5 accidents per month. They're looking at whether a trading estate's had any impact on the number of accidents. So within the first month afterwards, we are going to say that we're going to accept the alternative hypothesis if there's greater than 7. So to find the size of the test, what we need to do is to calculate it like we would do normally, greater than 7. So we'd Poisson, so it's going to be a 1 minus. So then we've got our sort of real significance level and the size of the test. Now find the power function for the test and sketch the graph of the power function. So if we have a look here, we're looking at 1 minus the probability that x is less than or equal to 6. So we're just then going to substitute different values in for our value for lambda. So we do it with 4, we do it with 5, we do it with 6. And then we plot these values to look something like this. Like it says here, we might have to do that with a partially completed table. We might have to just work out a couple of the powers or just one of the powers. There's nothing particularly different from what we were doing last lesson, apart from that you just need to maybe do it 2 or 3 times to generate all of the values for the power function and then have a go at plotting them. Okay, so quite a few things happening in this question. So we're going to compare two tests. So the first thing we should do is note that if we're comparing two tests, you should recommend the test with a higher power within the likely range of the parameter. So we're going to do some work here. It's slightly different, this, in that there is a manufacturer who is providing sweets to a shopkeeper. They say 40% of hard centers. The shopkeeper thinks that they're wrong. He sets up a H0 and a H1. P is less than 0.4 is his hypothesis for there, so it's going to be a one-tower test. Now, what's different for here is that essentially it's telling us what our critical region is, rather than saying, I want this significance level, and can you work out what the critical region is. It's telling us what he's going to do, and so we don't have to worry about what the significance level is, only like the actual significance level, which we're then going to use for the size of the test. So in this first one, he rejects if the number of centers is less than 2. So to find the size of our test, we just need to find the probability of getting less than 2 in a sample of 10. It's binomial in this particular case, so less than 2 probably is 0.4, gives us that as our size of this test. Part B. So for part B, we need to now do the power function of this test. So essentially, it's going to be the same thing, but we just don't know this P is 0.4. So we want to do the probability that we get 0 hard centers and the probability that we get 1 hard center and add those two together. So probability we get no hard centers is 1 minus the probability of getting a hard centre to the power 10, and then the same thing here, this is the probability of getting one hard centre, and then we're just adding them together. Then do the next thing he says I'm going to do a different test. This time I'm going to do a random sample of 5. If there's no hard centres, then we're going to reject H0. If there are some hard centres, I'm going to do a second sample, and if there's no hard centres in this, then we're going to reject H0. So to find the size of the test, what we need to do is we need to add together two separate things. We're going to first of all say the probability of getting no hard centres in the first test. And then this is where it gets a little bit trickier. We're going to say that we have to get some hard centres in the first test, so greater than 0. So we're just going to do 1 minus the probability that x equals 0, and then we get 0 in the second test, which is this second part here. I'm sorry, not second test, second sample. So then we can go through and work that out. The textbook is slightly wrong here. We should get 0.1495. You'll notice this has got quite a higher value for the size of an actual significance level. Now, again, I think it's quite important to notice essentially what we're going to be doing for D for finding the power of the test is doing exactly the same thing, except for in the part here where we've got 0.6, we're just going to be replacing my 0.6 with a p. So we go through and do exactly the same thing, and we're just replacing 0.6 with 1. Well, sorry, not replacing it with p, replacing it with 1 minus p, because in the 0.6 example, we've done 1 minus 0.4. And that will always be quite similar when we're going between functions for size and then the function for the power of a test. It's always just going to be replacing the value that we're given in the question with a generic p-value. For E, we want to find the values of R and S, so we just need to substitute those values into what we had for finding the power of the test up in part B. It says D here, but it should be going back into test A, which is part B. And then F, like we said at the beginning of this slide, we look for which one has the higher power value. If we look at every single different value of 0.23, 2.5, and 0.35, all of them, P has a greater power value than A, so we would be recommending for him to use test B. What I'd like you to do now is there's another geometric example in the textbook that you can have a read through, and then I'd like you to have a go at working through exercise 8D. For now, if you could leave the mixed exercise because we haven't done exercise 8B because of normal distributions. If you could just leave that and we'll come back to that a bit later. A reminder that on Wednesday we are going to be having a tutorial at 1 o'clock over Zoom. So please try and come along to that if you possibly can. Thanks a lot.